Hi everyone, welcome to part 3 of this CFD tutorial series on modeling external compressible flow in Ansys Fluent. In this video, I will go through the post-processing of a transonic turbulent flow around the wing at a 3.06 degree angle of attack and Mach number of 0.8395. I will visualize Mach number contours, identify shock locations, and analyze the pressure coefficient distribution. So if you haven't watched part 1 and part 2 yet, I recommend checking those out first to see how we mesh the geometry and set up the simulation. So let's get started. First of all, I will just go to mesh display and display the mesh here. I can show like this, but for a better visualization, I can go to view and under the graphic compose, I'm just going to transparent this pressure far field, which is around the wing. So I will just select here, display, and then I will uncheck the edge and this node and this parameter edges. And then I will increase the transparency to 70%, and then I will apply. So I can close this window. I can go here to isometric view, which is now here. So this is the geometry here. This is the wing that we are going to analyze. First of all, we will start with the Y plus. Now, let's take a quick look at the Y plus values, which are important for resolving the flow near walls. Actually, Y plus is a non-dimensional parameter that depends on the mesh resolution near the wall, fluid properties, and wall shear stress. Actually, it defined only in the first layer of the cell next to the wall here. So for this simulation, we use a relatively coarse mesh with a target Y plus value around 100, which is suitable for wall function approaches. So this helps Fluent apply the right near wall treatment when using turbulence model like SSDK Omega. So let's go to create a contour for this Y plus. So I will go to the result. And under the graphic, I need to create a contour. I will click on contour and then create a new contour. I will select this one. So here, I will write the contour Y plus for the name, and then I will disable the node values. And after that, here in the contour of, I will select the turbulence because the Y plus is under this turbulence. Then I can select the Y plus, wall Y plus. So I will select this one. And then here I will select wing bottom, wing edge, and wing top, which is the surface of this wing. And if I go to the outline view, you see I don't have any contour, but when I select on the display and save, I will have a contour here for this Y plus. So I will do it. I will just click here. Now I have a new contour, this contour Y plus. So now I can close this contour window, and this is the value of the Y plus here. So now you can see how it varies along the wing surface. Okay, so this is the Y plus value you can see here in this contour. Now it's time to plot the pressure distribution on this wing. So again, in the results under the graphic and contour, I will create a new contours here, select new one. So I will call this contour as contour pressure, And then here I will select the pressure and select the static pressure, which is the default setting here. Then I will change the coloring to banded, and then select the fluid symmetry, and again all the wing part, wing bottom, edge and top. And then I can save and display. I have another contour here. You will see the pressure contour. Just one note regarding this coloring setting. Actually, this banded coloring actually shows discrete color bands, like some steps between value ranges. So we use it to distinguish value ranges in this contour plot. So as you see, there are some banded here. So you can see if I change to smooth, it's a smoothing. It will, I mean, it is the coloring is like a smooth coloring without not without any distinguish. But when you choose the banded, you will see there are some banded that will distinguish the coloring on your selected surfaces, like this one. So in this case, I will select this one. I will go to the isometric view again to see the whole domain here. Then I will select this zoom window to go a little bit near to the wing again, and you see the pressure distribution contour here. Okay, I will close this one. So now we have these two contour for Y plus and the pressure. Now it is time to create a plane near the shock region. So let's go through this part. I will go to the result again, and under the surface I will create a plane. There are a few options here, so I can select this plane option here. If I just zoom out a little bit, you will see a preview of this plane. I will call this surface as the plane ZX because it will create in the ZX plane. And then here I will select ZX plane. So this preview will be changed. If I go to isometric view again, you will see it is in the ZX plane, this preview of this plane. And I will enter 1.11 for this Y value here. Okay. This value 1.11 corresponds to the Y coordinate at around the shock region near the tip of the wing. You can also click on this select with mouse to select a point from the graphic window. But in this case, I will just write the number here by myself, and then I will create a plane. So one plane will be added here in the surface. So I will do it, click create, and then I have this plane ZX here. Okay, so I will close this window, and now it's time to plot the Mach number distribution on this plane on wing near the shock region. So again, in the graphic, I need to create another contour. I will go to contour, click, and then select the new contour. This time I will call it as contour Mach, and then here I will select the velocity to find the Mach number. Here it's available, so I will select the Mach number, and this time I will select the plane ZX that I've recently created and change again coloring to banded type. So now it's time to create this contour. Okay, so I will close this window, and this is the contour of a Mach number. You will see the range of the Mach number. So it's a transonic flow over this wing. So, but let's have a better look on this one. So we create the ZX plane. I can select another view. If you see here, we have Y direction. I will select the Y plus direction. So here I have this one. I will select this tool, zoom to area, and then just select this area here. Okay. So note that discontinuity in this case is shock on the upper surface of this wing. It's completely visible in this contour here. Okay, so we can go through another contours like the velocity contour to check again another contour. So I will go again on the contour, select a new contour, call this as a contour X velocity. Just ensure that this fill is enabled in this option. Enable again the banded options as I explained before, and the under the velocity I will just select the X velocity here, and then select this created plane, ZX plane, and then save and display. Okay, just let me open it again, this window. So now you can note the flow reversal downstream of the shock here in this plot also. Okay, after creating these contours, now I will go to create a vector again under the graphic, this time vector and a new vector. So I will select the vector here, and I will call this vector velocity like this one. Here we will have a vector in a few seconds here. In this settings, I will select the velocity, and then here I will select the X velocity, select plane ZX here. Then I will save and display. In this case, I need to change this value scale, for example, to 0.5. It is still not proper value. I will decrease the size again, this scale to 0.05. I will display. So now we have a velocity vector here. Then I can zoom in this area a little bit. I can close this window here, and now you can see these nice vectors around this airfoil, and so the flow reversal is clearly visible here in this velocity vector. Okay, so you will see the increase of velocity here, and then decreases again the velocity vector in this x direction. Okay, so now I will go to create two isosurfaces near the shock region. Then I will generate two plots from these isosurfaces. So here I need again go to the results and create, but this time I will select the isosurface here. Okay, in some other previous videos, I explained how we can create isosurface. Here again, I will create another one. So for the name of this surface, I will call it as the ISO Y button. Okay, and then here I need to select the mesh, and then I can go here and select the Y coordinate. So here, this green one is the Y coordinate. So I will select here, and this ISO surface is generated from the wing button surface here. So I will select this one. Then I will click on the compute to get my minimum and maximum value of this Y coordinate here. And then here for the ISO values, I will write the 1.11 meter here. And as I said before, this value corresponds to the Y coordinate at the shock region near the tip of the wing. So now I can create this surface, ISO surface. So now I have this ISO surface here. Okay, and now as I have this one, ISO Y bottom, similarly I will create a surface for the top surface, and I will call it as uh, ISO Y top. Again, the same process, but this time this surface will be for the top surface of the wing. So I will select this one, and then again compute, and then put the value here. I will create the ISO Y top for the next ISO surface. Okay, now I will close this window and go to create one XY plot here under the plot. I will go to XY plot and then create a new XY plot. Okay, in this case, I'm going to create some XY plot for the wall shear stress. I will call it as XY, then X shear stress for this XY plot name here. And then under this Y-axis function, I will just go directly to the wall fluxes in the here X wall shear stress from this part, and then select these two ISO surface that I have recently created, ISO Y bottom and ISO Y top, from this surface selection list, and then I can just click on the save and button and close this dialog box here. I can close this window, and now you can see the X wall shear stress on Pascal. This red dots for the top surface, and in the bottom surface, which is this white dots here, you will see the wall shear stress as shown in this picture. Actually, the large adverse pressure gradient induced by shock causes the boundary layer separated. So here the point of this separation is where the wall shear stress vanish here, and the flow reversal is indicated here by this negative value of this X component of the wall shear stress in this XY plot. So we have many different type of contours, vectors, and also this plot to analyze our compressible flow and this shock and this type of simulation. So you can use it for yourself and for your case to find your flow reversal where the shock will happen, and that these are very useful post-processing tools that you can use. So now I will just go and write the case and data here again, and then I can Save it as another font, 02 in my case. So as a summary for this tutorial has been divided in 3 parts and demonstrate how to set up and solve an external aerodynamic problem using polyX core meshing in Fluent meshing, and then in the Ansys Fluent we use the pressure-based couple solver with under relaxation from a pseudo time method, and also the K omega SSD turbulent model. So I hope you gain some new tips here in this playlist and this series. So thanks for supporting and watching this video.